for those that wants to watch the replay, we can be able to. All right, so I welcome you to today's class once again. In our last class, we look at question number 2 that falls under energy, work, and power. And I must commend those that have marked their assignment. You guys really did well. At least we have somebody who scored 23 over 28. And I think the least score we have is 16 over 28. That's a very good performance for a start, but we can do better. Are you getting it now? So all you just need to do to pass jamb is get yourself familiar with questions. Like, it's very, very important you get yourself familiar with questions. The more questions you are familiar with, the faster you can solve in exam. Are you getting it now? So those questions, try and go over it again. Look at the ones you fail. Then ask yourself, why did you fail it? So that you can implement your correction. Is that taken now? And whichever one you are still finding difficult, you can reach out to me. I'll definitely be there to put you through. So we are moving to the next question, which is question number 3. And the question states that 2 balls, X and Y, weighing 5 grams and 50 kilograms, respectively, were thrown upward vertically at the same time with a velocity of 100 meters per second. How will their position be 1 second later? So when you look at this question, it's strictly under the topic gravitational field. Are we together now? It's under the topic gravitational field. For that reason, we are going to start by looking at gravitational field in today's class. So without any further ado, let's move to our board. All right. So we want to look at what we refer to as gravitational field. Okay, sorry, I cannot see that. So gravitational field. Now, when you talk about gravitational field, what are the things that examiner want to test under this particular topic? Number 1 is that examiner wants to test if you understand force field. Number 2, examiner wants to understand if you understand gravitational field itself. And number 3, examiner wants to understand if you understand what we call field strength. Number 4, under this same topic, examiner wants to understand, they want to test if you understand the concept of acceleration due to gravity, potential energy on a gravitational field, and kinetic energy on a gravitational field. They want to understand, they want to test if you understand the concept of acceleration due to gravity, if you understand the concept of potential energy of the field, and the kinetic energy of the field. Examiner wants to understand examiner wants to test if you understand the relationship Oh, sorry, I think I have not presented my screen. Sorry. Thanks for calling my attention to that. So can you guys see the screen now?
Yes, sir.
I'm sorry, thanks for calling my attention to that. Yeah, so examiner wants to understand if you know the concept of the mass of an object the weight of an object, if you understand the relationship between them. And lastly, examiner want to test you on two things, what we call orbits and satellites.
Why is it like this?
Orbits, and lastly, weightlessness. Weightlessness. All right. So under these areas, they are what you want to know as far as gravitational field is concerned. You want to understand force field. You want to understand gravitational field itself. You want to understand field strength. You want to understand acceleration due to gravity, potential energy, and kinetic energy that has to do with gravitational field. You also want to understand the concept of mass and weight, the relationship between them. You want to understand what we call orbit and satellite, and lastly, weightlessness. So how can we summarize this? That is going to meet the requirements of what JAMB will be asking us about all these topics, all these headings. So let's start from the very first one, what we call force field. Now, when you talk about force field, we have force field when we are looking at the word force itself. When somebody says force, what is force? Force is an external agency that changes or tends to change the position of an object. Am I making sense now? An external agency that changes or tends to change the position of an object. It's now divided into two. It's divided into what? Two. We have one, contact force, and we have two, force field. Please mute your mic. Please kindly mute your mic. Everybody should mute their mic. You can only unmute your mic when you want to ask question. Thank you, so that we can reduce the noise as much as possible. All right, so back to what I'm explaining. So force itself is divided into two, contact force and force field. You see, when you say contact force, you are talking about force that are not conservative. Are you getting this now? Forces that are not conservative. And when I say force is not conservative, it means that force, if it should cause increment, the force cannot cause decrement. Are you getting this now? If the force increase something, that force cannot decrease it. And if the force decrease something, it cannot increase it. Those kind of force, they are called forces that are not conservative. And example of such forces include what? Contact force. So when you say contact force, we have example of contact force to include push, what we always refer to as like force. We have what we call pull, what we refer to as unlike force. And we have the last one that we call friction. And when you say friction, we can also call it viscosity. Now, friction, we call it friction when we are looking at a force that opposes motion of an object in solid. When you have a solid material and you have a force that is opposing motion of an object, that force is called a frictional force. But if it happens to be in fluid, when they say fluid, fluid simply means they are talking about either gas or they are talking about liquid. So when you are considering friction in any of these two, you refer such frictions to what we call viscosity. So we rarely consider friction in gas. Are you getting this now? We mostly consider it in liquid. Whenever we are trying to consider friction in gas, that is what we refer to as air resistance. Now, we have understand the branches of the contact force. Now, let us look at that of force field, which is what we really want to look into. Okay, so when you say force field, you about the following. You know, we say contact force is divided into three: push, pull, and frictional force. But when you say force field, it's also divided into three. We have what we call electrostatic field. We have magnetic field. We have magnetic field, and we have the third one, which is a gravitational field. Are we together now? So when you say electrostatic field, you are talking about electricity. When you say magnetic field, you are talking about magnetism. When you say gravitational field, you are talking about what? Gravity. Am I making sense now? Now, before I go into all this, of course, I won't really go deep here, but I'll go to some extent because of some questions that JAMB always bring forth between all these three fields. Now, let's define what we call force field. When you say force field, what does it mean? A force field is a region under the influence of some physical agency. I'll take it again. A force field is a region under the influence of some physical agency. So when you say force field under the what? Influence of some physical agency, you can divide it into two. It can either be what? A scalar or a vector. So if it is a scalar field, you are talking about temperature, you are talking about thermal energy. Are you getting this now? You are talking about electrical potential and so on. Those ones, they create what we call a scalar field. But when you talk about vector field, that's when you can be talking about electrostatic force, you can be talking about magnetism, you can be talking about gravitational field. These three fields, they are vector fields, meaning that they have magnitude and they have direction. Now, when you talk about electrostatic field is a region or space where a body experiences the influence of some electrical force. Are you getting this now? A region where a body experiences the influence of some electrical force. Now, in this field, there is what we call force of attraction. Force of attraction. What we call force of repulsion. There is force of repulsion here, there is force of attraction here. Are you getting this now? The same thing goes to magnetic field. A region or space where body experience the influence of some magnetic force. Here also, there is what? There is force of attraction, there is force of attraction, and there is force of repulsion. Are we following? But when it comes to gravitational field, we said it's a region or space around masses. Are we there? A region or space around masses where they experience the influence of gravitational force of attraction. So under this field, the only thing that happens there is a force of attraction. Are you following now? So if you are comparing gravitational field with magnetic field and electrostatic field, you should know that in electrostatic field, there is what? Attraction and repulsion. In magnetic field, there is attraction and repulsion. But in gravitational field, we only have attraction. It's only attraction that takes place in gravitational field. There's no repulsion. Because JAMB will want you to compare these three fields. And in one of the way they compare them is by their force. So you know now that electrostatic force, repulsion and attraction, magnetic repulsion and attraction, but gravitational, it is only attraction. Another thing you should know is that electrostatic, it has to do with what? Electric charges. It has to do with electric charges only. Why? Magnetic field has to do with elements with magnetic molecules. Magnetic field has to do with elements with magnetic molecules. Why? Gravitational field only deals with mass. Are you guys getting this now? Please, are you getting the explanation?
Yes, sir.
So,
Yes, sir.
electrostatic field only deal, sorry, gravitational field only deal with mass. Are you getting that differences now? So you'll be able to compare them easily by knowing all of this. Again, electrostatic field deals with attraction and repulsion. Magnetic field deals with attraction and repulsion. Gravitational field deals with only attraction. Electrostatic field deals with only what? Charge. Magnetic field deals with magnetic molecules. Why? Gravitational field deals with mass. Please mute your mic. Please mute your mic. Once you finish responding to question, mute your mic. It's always disturbing. Thank you. So do we get that clear now? So that's the comparison within those fields. All right. So let's quickly look at the gravitational field in detail. So let's look at that in detail. Gravitational field now. So while we are looking at this, I'm going to start, I'll by His grace be pointing out how JAMB will want to question you under this field. Are we together now? So when you say gravitational field, how do we come about this field? And what do we need to know about the field? You see, everything about this field is as a result of the postulate of scientists in the early time of the universe. A scientist called Plato, he discovered that, you see, it is the earth. He said what? The earth is at the center of the universe. Let's say this is the universe. He said it is the earth that is at the center. Why other planets, they are revolving around the earth. Are you getting this now? A lot of scientists supported this postulate, and this postulate is called heliocentric model. But later, a scientist called Nicholas Copernicus challenged this postulate that it's not correct. Earth cannot be at the center of the universe while other planets revolves around it. Instead, it is what? It is the sun that is at the center of the universe while other planets, they revolve around the sun. And we have the postulate now to be that it is the sun that is at the center of the universe. Other planets, they revolve around the sun. And this postulate is called geocentric model. I want you to pay attention to all this. They look insignificant, but they can be tasky. Are we together
Excuse
now?
me, sir.
I'm listening.
I missed the geocentric model. Who brought it, sir?
Nicholas Copernicus.
Okay, thank you, sir.
Yeah. So he said it is the sun that is at the center of the universe, and we call this geocentric model. So a lot of scientists support this postulate, and they all agree. So after some years, a scientist called Tycho Brahe now said neither the sun nor the earth is at the center of the universe. but the sun is the leading planet, while other planets they queue behind it. So what he said is that the earth is not spherical. Are you getting it now? Or the earth is spherical, but the sun is the leading planet. Every other planet, they are moving behind it. So this postulate look kind of awkward, and nobody supports the postulate. Now, they now come back to this geocentric model and try to look at the deficiency of this model. The model already let us understand that the sun is what is at the center of the universe and other planets are revolving around it. But this theory did not specify the position that we have the sun. Is it perfectly at the center, or it's not perfectly at the center? That is the deficiency of this law. The law fails to explain that. So a scientist called Kepler, the name of the scientist is Kepler. Kepler now stated 3 laws that you might be questioned on. These 3 laws that we refer to as Kepler's laws, the first law states that, Kepler's first law states that the planets describe ellipse of the sun as one focus. Are we together? Kepler's first law states that the planets describe ellipse of the sun as one focus. What's this law stating? This first law is coming towards to support geocentric model. That is, it is true. It is what? It is true that the sun is at the center of the universe. But for other planets to set it up as one focus, it means it's closer to some planets than another planet. You will understand this if you have taken a course on what's it called? Conic section. If you have done conic section, that is equation of circle, ellipse, hyperbola, parabola. So you understand what I'm trying to say here. So for him to say that the planet describes what? The ellipse of the sun as one focus, that means the sun is closer to some planets than other planets, though it is at the center. So that's the first law. Then the second law now states that the line joining the sun, and the planets, sweep out equal areas in equal time. The lines joining what? The sun and the planets sweeps out equal area at what? At equal time, or in equal time. Anyhow, what does this mean? What this law is trying to tell you is that, you know, look at this planet that I have here. Let me call this planet A, planet B, planet C, planet D, planet E. Please pay attention. If you look at this, you see that planet C, planet D, and planet E, they are closer to the sun. But planet B and planet A, they are far from the sun. So what this law is telling you is that any planet that is closer to the sun tends to move faster than other planets that are far from the sun. So what does that mean is that by the time they keep moving like this, whenever C gets closer to the sun, it moves faster. Likewise this. So A and B would also at a point get closer to the sun, and then they will also move faster at the same rate. So that law is explaining to you what happens when a planet is closer to the sun and when it is far from the sun. Then the third law of Kepler. The third law now states that the square of the period of revolution of the planets are proportional to the cube of their mean distance from the sun. So In a nutshell, what this third law is telling you is that all these planets, they are moving at equal rate, at a constant rate, like it's a constant speed that they are moving with. Am I making sense now? So these are the three laws stated by Kepler. Now the question now is, what are the deficiency of these three laws? The deficiency of these three laws is that they fail to tell us what makes the planet to be moving. You know, the law described that the Earth is not perfectly spherical. It has let us understand that the sun is closer to some planet than other. It's not perfectly at the center. Are you getting this now? And it has let us understand what happened, the relation between their speed and time. Now that this law gives us this explanation, what exactly is making all these particles to move? The law fails to explain it. So as the law fails to explain it, that becomes the deficiency of Kepler's law. And that is why we now have what we call Newton's laws of universal gravitational. Newton's law of...
Excuse me, sir.
I'm with you.
Do Kepler laws apply to all planets? Does it apply to all planets?
So when you talk about the planets, you talk about the universe, it applies.
Okay.
It applies to all planets. So Newton's law of universal gravitational now come to explain the deficiency in Kepler's law. Remember, we said the deficiency in that law is that the law fails to explain why the planets are moving. So, what does this law state? Newton's laws of universal gravitational states that the force of attraction between two masses, it can be any two masses, is directly proportional to the product of their magnitude and inversely proportional to the square of their distance apart. You get the law? I'll take it again. Newton's law of universal gravitational states that the force of attraction between any two masses is directly proportional to the product of their magnitude and inversely proportional to the square of their main distance apart. That is what the law states. What is this law trying to let us understand? The law is letting you understand that what makes all these planets to keep moving without stopping, without meeting each other on the road, is as a result of the force of attraction between them. They are attracting one another. That force is what set them in that circular orbit. What we refer to, we can say the force is equivalent to a centripetal force. Are you getting this now? So it is the force of attraction between those masses that keep them to keep moving. And this force of attraction will always be between any two masses. And that's why you'll be under the tree. At times, you just see that the fruit fell down. Nobody plucked it. It's just a result of the force of attraction of the earth. That is what attracts the fruits. Now, let us combine this. You know, this is the first statement of the law, and this is the second statement of the law. If you combine this together, you have that F is proportional to M1, M2 over R squared. And then we can conclude by removing this proportionality sign that F is equal to G M1 M2 all over R squared, where G is gravitational constant. So we said G is gravitational constant. That means it has a constant value that will not change. Am I making sense now?
6.67 times 10 raised to power minus 11.
So that is 6.67, or you can say 6.7 multiplied by 10 raised to power minus 11 Newton meter square per kilogram square. That's the value of that gravitational constant. Now, is there any other name for this law? Yes, there is another name for the law. The law is also called inverse square law. The law is also called what? Inverse square law. So, inverse square law. So, examiner can put it to you that which of the following is known as, or they can state the law for you. In most cases, they do that. They will state the law for you. That is, force of attraction between any two masses is directly proportional to what? To the product of their magnitude, and inversely proportional to the square of their main distance apart. You see, they will not ask you that, which law is this? They will not tell you that it is universal gravitational law. Are you getting this now? You have in your option inverse square law. So if they said inverse square law, you should know that they are referring to this law. But in physics, there are two laws that we refer to as inverse square law. Are we together now? There are two laws that we refer to as inverse square law. And what are these two laws that we refer to as inverse square law? The universal gravitational law and the Coulomb's law. You know, the Coulomb's law states that the force of attraction or repulsion between two charges is directly proportional to the product of their magnitude and inversely proportional to the square of their main distance apart. You just see that it is the same thing as the law of universal gravitational law. That's why we call those two laws inverse square law. So please take note of that. It's very important. All right. So what other things do you need to know here? So let's take a proper explanation of this law. Now, what are the things you want to know about this? Because under this equation, that is where you have, let me say, 90% of, let me say, okay, I think I'm exaggerating much. Let me say 70% of questions that examiner will want to ask you under this topic, it lies with this particular law. How do they ask? Number one is that examiner wants to know if you understand the reason why this force is not really affecting us. Because if you look at the planets, here is the sun, and these are other planets like Earth, Jupiter, Venus, and the likes, Mercury and the likes. When this one moves, because this one moves, it attracts this one to move. So because this one moves, it attracts this one to move. Because this one moves, it attracts this one to move. Because this one moves, it attracts this one to move. Because this one moves, it attracts this one to move. And this one is moving, is attracting this. And that is how they continue moving like that. But the question now is, why is this force not affecting me and you? If I move, you don't necessarily need to move. You can still remain in the same position you are. If I move, the chair beside me will not move. The table beside me will not move. And they have mass. The reason why it's not happening like that is because my mass, your mass, the table mass, the chair mass is what? Very small compared to the mass of all these planets. So when you look at the mass of this planet, it is very what? Huge. Therefore, the force of attraction between them is also what? Huge. Are you getting it now? So the higher the mass, the higher the force of attraction. Are we together now? The higher the mass, the higher the force of attraction. Now, what other thing affects the force? You know, we've said that the mass affects the force. If the mass is very high, the force will be high. Another thing that affects the force is the radius. That is, I say radius, the distance between the two objects. If I have an object mass m1 here, and I have mass m2 here, if the distance between them is 100 meters, and I have another mass m1 and m2, and the distance between them is just 10 meters, the force of attraction between this one is going to be greater than the force of attraction between this, because the higher the distance apart, the lower the force of attraction. Are we together? Now, what other things examiner would like to ask you under this force? At times, examiner can give you question that if the mass, I get this now, if the mass of an object, if the mass of an object is doubled, what will be the effect? What will be the effect on the force of attraction? Now, I want you to know that they can ask this in any way, but it's just like they are telling you, like, okay, if I double the mass, what will happen to the force of attraction? If I triple the mass, what will happen to the force of attraction? If I reduce the mass by 4, what will happen to the force of attraction? How do you check? This is how you check. If you want to know what will happen to the force of attraction when you double the mass, just write down this equation. Write this as m squared. That is, assume that the mass is the same thing. Just write it as m squared instead of m1, m2. Then all over r squared. Are you following now? And you are told that if you double the mass, let's say this is the mass, and now the mass is m1, and m1 is equal to m. So when you double this, you know, you are going to be having 2 of m. Am I making sense now? So if you have 2 of m, every other thing that is not mass in this equation, make them to be 1. That is, g will become 1, r will also become 1. So you now have that f is equal to 1 multiplied by m will now be 2m squared divided by what? 1 squared. Are you seeing it now? So you see that f will become 4m squared. So that means if you double the mass, the force of attraction would increase by 4. Are you getting this now? When you double the mass, the force of attraction will increase by what? By 4. Okay, class, I want to ask, if I triple the mass, what do you think will happen to the force of attraction? What will be the effect? Is somebody doing something?
It will
It will
increase
increase.
by 9.
It will increase
It will
by
increase by 9.
9.
It will increase by 9.
So do you understand
By
that
9.
now?
Yes,
Now,
sir.
Yes, sir.
if I now say I decrease the mass by 2, mind you, when I say decrease, it doesn't mean minus. It means division. If I say the mass is decreased by 2, that means I divide this by 2. I see it now. Then you have that f is now equal to m all over 2 all square. You know, g will be 1, r square will also be 1. Are you getting it now? That means f value will now be m square all over 4. And that simply means that the force decreased by how many? Decrease by 4. So when you reduce the mass by 2, the force is going to reduce by 4. So let's check how distance affect the force. How distance affect the force. So if I double the distance, what will happen to the force? Remember, the equation remains this. So if I double what? Let's say R1 is equal to R. So if I double this now, I have to double this also. Abi? So this equation will become F equal, remember, anything that is not distance this time around will become 1. That means that G and M squared, they will become 1. So I'll be having 1 all over R squared will now become 2R all squared. That will give me 1 all over 4R. Have we seen this now? That's to tell you that if I double the distance, I will reduce the force by 4. And so on like that. So that's how you check for the relationship. Now, what other thing do you need to know about this force? Another thing you need to know about this force is that this force is constant on every object, irrespective of their mass. I want you to pay maximum attention to this very well, because JAMB can be tricky. They can ask you questions under this particular one I want to explain now in different way. They can give you a lot of values thinking you have something to do, but you don't have anything to do. Just understand that if you have objects on this earth, and let's say you have on an object of 500 kilograms and you have object of 1 gram, you can see the difference between them. If you throw these objects at the same time, if you throw them at the same time, because the force of gravity is equal on the two objects, they will come down at the same time. Are you noting that? If you launch the two objects at the same time, they will do what? They will reach the ground at the same time. And if they reach the ground at the same time, that means they both attain the same distance. Their distance will be equal. Let's take for instance that I have, this is an height, this is the base, and I'll throw these two objects from here. You know, this one is very, very big, and this one is small. I throw them with the same velocity. They will both reach this place at the same time. Am I making sense now? Irrespective of what the time might be, even if it is 1 hour later, they will get to the same place. Why? Because force of gravity is equal on them. Likewise, if you throw them at the same time, they will also reach ground at the same time, because the force of gravity is equal on them. Are you guys getting this explanation clear?
Yes, sir.
So JAMB might want to confuse you, giving you a lot of parameters that you might want to consider. You want to start asking yourself what formula to use and what. Don't stress yourself. Once it is this case, just know that the two objects will attain the same height at the same time, and they will come down at the same time. Now, that's for JAMB. In case we have YX students here, if YX should ask you this particular question under theory, you will be able to answer this question correctly if and only you take care of the two sides. Because you all agree with me that if I throw paper and I throw pen, if I throw them down, pen will get down before paper. But what the law of gravity is telling us is that they're supposed to come down at the same time. That's true. They will come down at the same time. But what prevents paper from coming down at the same time as the pen is because air resistance is affecting the paper. So if that should happen in vacuum, they will get down at the same time. So for YX students that want to respond to this question, YX students should respond to the question by saying what? If it happens under air resistance, the one with high mass will come down first because of air resistance that will affect the one with the low mass. But if it should happen in vacuum, the two bodies will come down at the same time because the force of gravity is equal on every object irrespective of their masses. That's how you respond to that as a YX student. But as a jamb, just know that they are not telling you to consider either air resistance or no air resistance. And you can also pay attention to what the question is stating. But just understand that the theory states that they are coming down at the same time. Do you understand that now?
Yes, sir.
All right. So note that equation. We have that for us to calculate the force of attraction between two masses, we have that F is equal to gm1 m2 all over r squared. Now, what other things do you need to know? We need to know about the field intensity. How to calculate the field intensity of a gravitational field. The question is, what is field intensity? They might not call it field intensity at times. They can call it what? Gravitational field strength. So either they call it field strength or they call it field intensity. They are referring to the same thing. And it is a vector quantity. So field intensity is defined as the force per unit mass. I'll take it again. Field intensity is defined as the force per unit mass. That's to tell you that E is equal to F divided by mass. Now, you use this formula if you are given force and mass. That's when you use this formula. But if you are not given force and mass, maybe the examiner give you the mass of the earth and they give you the mass of the objects. How do you calculate for, and they give you the distance of the object away from the earth? How do you calculate for the gravitational field strength? You say, recall that F is equal to Gm. Let me just say this is just M, mass of the earth, and this is the mass of the object, divided by r squared. So use this one to replace F in this equation. You have that E, which is the field intensity, is equal to Gm, let me say this, divided by r squared, multiplied by 1 all over m. So that this m can cancel this m. You therefore have that field intensity E is equal to Gm all over r squared. Do you understand this now? So this is how you can calculate for what? That is, oh, sorry, I think, yeah, okay, so this is correct. So this is how you can calculate for what? The field intensity. Am I making sense now? So this can be mass of the earth, it can be mass of the object. Depends on what the question is stating. Is that taken now? So this is going to be the field intensity. All right. So if I have this as the field intensity, and I have this as also the field intensity, so I can use any of the two equations depending on the parameters given in the question. Now, the next thing you need to understand how to calculate here is what we refer to as gravitational potential. Gravitational potential. So what do we call gravitational potential? Gravitational potential energy is the work done. Are you taking note of that? Gravitational potential energy is the work done in taking a unit mass. The work done in taking what? A unit mass from infinity to a point on the earth. The work done in taking a unit mass from infinity to a point on the earth. Are we there now? And you can also define it. You can also define it as work done when mass are moved from one point in a gravitational field to a higher point. Are we together now?
Yes, sir.
Now, at times, when you see this equation for gravitational potential, we have that V is equal to, this is the formula for gravitational potential. We have V equal to Gm over R. Are we together now? Where m is mass, g is the gravitational constant, and r is the distance apart. Now, in case whereby you are having this equation to be v equal negative gm over r. Because examiner can what? Can ask you that what is the significance of that zero? Are we together? If they ask you,
Yes, sir.
if they ask you that what is the significance of this negative sign, so The negative sign is telling you that what? The work done in taking a unit mass from infinity to what? To a certain point on the earth is what? Is less. Are you getting this now? Is what? Is less. Or in a nutshell, as a y-axis, you can say it signifies that the work is done by taking what? A mass from infinity to a point on the earth. So that is the significance of that negative sign. Do you understand that now?
Yes, sir.
So if you want to explain it better, you can also break it down and say the work done at infinity. Note very well. The work done at infinity. Work done at infinity is 0. Are you getting it now? Is greater than on Earth. That's the essence of the negative. The work done at infinity is what? Is greater than the work done on Earth. That's why you have that negative there. The negative is not affecting your value, but it's showing that the work done at infinity is greater than the work done on the Earth. That's why you have that negative sign in front of that equation. Do you understand that now? Okay? So the next one that we need to understand here is the kinetic energy. The kinetic energy. Now, when you talk about the kinetic energy, we are talking about the work done in taking a unit mass from the Earth to infinity. Are we there? The work done in taking a unit mass from the Earth to infinity. That's what we refer to as the kinetic energy. Are we together? And then we can have the equation to go in this way. Kinetic energy is equal to 1/2 mv squared. 1/2 what? mv squared. So if this is what I have as my kinetic what? Energy, then I can modify this equation to become kinetic energy equal GFM all over 2R. And okay, yeah, so if I have this, I can also what? Describe kinetic energy as what we refer to as escape velocity. Are you following? Now, when you say escape velocity is like the opposite of the gravitational potential. The work done in taking a unit mass from this Earth to a point at infinity. And we have it to become V equal the square root of 2GR. Or you say V equal the square root of 2GM all over R. Or you said that V is equal to 2 times potential energy, 2 times potential what? Energy divided by M. So these are equations for escape velocity. Now, before I move on, let me quickly explain something about this escape velocity. It has a constant value. And you will all agree with me that when you throw something up, that thing will surely come down. Is that true?
Yes, sir.
Yes, sir.
Normal.
Okay, normal. All right. But what really was the factor that responsible for this? The reason why when you throw something up, that thing will surely come back is because the velocity that you use to launch that particular thing is not enough to help the body to escape the gravitational influence of the earth. Are you getting this now? So because that velocity is not enough to help this body to escape the gravitational influence, that's why you see the body pulling back. But if you launch this body with a velocity called escape velocity, so for example now, if I come down to this equation now and I replace the g with 9.8 and I replace the radius with the radius of the earth. So if I put that into this equation, my result will be about 11.3 kilometer per second. This 11.3 kilometer per second is what we call escape velocity. So if you launch a body with this kind of velocity, the body will go and it will not come back. That's the kind of velocity that they use in launching satellites. That's the kind of velocity that you can use to launch a missile. Are you getting this now? So this is called escape velocity. If they launch you with this velocity, you never come back to this earth again. That's called escape velocity. The value is constant, 11.3 kilometers per second. But at times, jamb might wants to confuse you. They can give you what? 11 kilometers per second. They take the approximate value. It's still what? The same thing. Do you understand that now? So that is escape velocity. Any value lesser than that is not an escape velocity. I believe we are taking all of these equations down. What do I quickly want to explain under this aspect of escape velocity is that a velocity, you know,
Sorry, sir.
I'm listening.
Sorry.
I'm listening.
What is the average velocity of a car that moves 30 kilometers in 3 hours?
What is the average
Velocity of a car that moves 60 kilometers in 3 hours?
60 kilometers
in 3 hours, sir. 3 hours.
3 hours? Who can help us to the solution to this class? Is there anybody that wants to help us?
That will be 20 kilometers per hour, sir.
Oh, thank you. You get the answer right
20
now.
kilometers per hour.
20 kilometers per hour. So thank you so much for that swift response. So when I say average velocity, hello, listen, when I say average of something, don't think they are always referring to half. Are you getting this now? On an average simply means like at max, what can you get? Let's take for instance that you are stranded now and you're looking for help. You get where I'm coming from now? Maybe something cost 50K. And they were like, on an average, how much can you like get? Like when you pack all your things you have, how much? That's what they mean by on an average. When I say average velocity, they are still referring to the same. So it's going to be total distance covered divided by the total time taken. Is that taken now?
Yes, thank you very much.
All right, you're welcome. So thank the person that give response to the question. Thank you. So let's move on now. Now, I told you earlier that when you launch a body with a velocity that is less than 11.3 kilometers per hour, per seconds, the body will go, when you launch a body with this kind of velocity, it will go and it will not come back. Somebody's saying something. I can't see that message again. Somebody's complaining about some people's video. I don't know. Maybe it's their network then. So let's go on. When you launch a body with this kind of velocity, it will go and it will not come back. That's what we call escape velocity. Now, there is a velocity that is lesser than this, that will cause the body to go, but it will not come back, and the body will not also escape the gravitational influence. The body will not come back, and it will not escape the gravitational what? Influence. Remember, escape velocity is the square root of 2g multiplied by r, where r is the radius of the earth. So if you put radius of the earth in this equation, you will have this value, 11 kilometers per second. But if I replace the radius of the earth with the radius of the moon, instead of radius of the earth, I put radius of the moon, and we have a velocity of 8 kilometers per second. When you launch a body with this kind of velocity, the body will go, it's not going to come back, and it's not going to escape the gravitational influence. So it will keep what? Moving around the earth. That is what we call orbital velocity. Orbital velocity. It will not go and it will not come back. So that's that about the aspect of escape velocity and orbital velocity. Now,
Sorry, sir.
okay.
A plane uses which velocity to escape the Earth, sir?
I can't hear what you say. Is the person still there? I can't hear what you are saying.
An aeroplane
Okay.
uses which velocity to escape the gravitational force of the Earth?
The aeroplane is not escaping the gravitational force of the earth. Is that taken now?
Yes, sir.
What keeps the aeroplane at a balance point is that the kind of velocity that it's moving with. I get it now. And that is why, okay, let me even go deep like that so that we will not take much time explaining that. If your aeroplane has a force that keep pushing that same velocity, that maintain that same velocity, that doesn't allow it to reduce. When that velocity reduce, you started seeing your aeroplane coming down. So that force that you have in the engine is what is maintaining the balance of aeroplane in space. It's not as if it's escaping the gravitational influence. Am I making sense?
Yes, sir.
Yeah. So if the aeroplane should escape the gravitational influence, then you are not going to see both the pilot and the plane and the people inside it again. Because there's no force that will pull them back to the earth. So that's that about that. All right, so I don't really want to waste much time here. But there's an aspect that WAEC or JAMB always want to wait for you when it comes to the placement of an object on the Earth's surface. Let's take, for instance, that this is the center of the Earth and this is the radius of the Earth. Are you getting it now? If an object is here, we are all assumed to be at the center of the Earth. Are you getting it now? So if an object is here, you consider the distance of the object from the Earth on the Earth to become what? The radius of the Earth. Am I making sense now? So if an object is above the Earth, remember, this is the Earth here, and you have this to be R. Above the Earth is above the Earth with an height h. Are you seeing it now? Are we there?
Yes, sir.
So what will happen to the distance of such objects away from the Earth is going to be h plus r. So that will be the distance used for such objects. All right. So we talk about orbit and satellites. What is orbit and what is called satellite? When you talk about orbit and satellite, you are talking about orbit. Orbit simply means the curved path of an object moving in space. When they say orbit, it means the curved part of an object that is moving in space. And when you say satellite, satellite simply means a small object moving in an orbit around a larger object, with the larger object exerting a gravitational force on the smaller object. Are we there? I'll take it again. Orbit means what? The curved part of an object moving in space. And satellite, a small object moving in an orbit around a larger object, with the larger object exerting gravitational force on the smaller object. Now, when you talk about this satellite of a thing, it can be natural and it can be artificial. It can be artificial. Now, when you say natural satellite, you are talking about the planet as the satellite of the sun. Because the mass of the planet compared to that of the sun is what? The mass of the planet is smaller compared to the mass of the sun. And the planets are revolving around the what? The sun. And the sun is what? Is exerting the force of gravity of attraction on them. Therefore, they are satellites of the sun. The same thing goes to what's it called? Another example of natural satellite is the Earth and the Moon. The Moon is the satellite of the Earth. It's also natural. Then when you say artificial satellite, you are talking about the spacecraft. Are you getting this now? The spacecraft, they are the example of artificial satellite. Now the question is, can they ask us question under satellite calculation? The answer to that is yes. Most times, the kind of question they always ask under satellite is the period. Are we together now? And when you are asked about the period, you go back to the, what's it called? This Kepler law. Then we have that t square, that is the period of the revolution. T square is equal to 4 pi square multiplied by the radius of the Earth divided by gravity. Are we together now? And if they are asking for the velocity of a satellite, of course, a satellite is going to make use of what? Escape velocity. Are you getting this now? But this time around, we are going to, I just call it escape velocity so that you can quickly what? Remember. So this is the velocity of a satellite. G square root of G R E. That is gravity multiplied by the radius of the Earth. Do you understand that now? So if you reduce this equation further, you can have this to become T equal 2 pi the square root of R divided by G. And this is very simple to the simple harmonic motion equation. Are we together now? So if this happens above the Earth, remember, if it happens above the Earth's surface, then you have that C is equal to 2 pi N, the square root of R plus H all over G. Are we together now? We are running out of time, so we need to move fast. Okay.
Sir, what's the N?
The N is the number of revolution.
Okay, sir.
Shall we go on now? So if you look at this equation now, you get to see that the period is independent of the size of the mass of a body. The period is independent. Either the mass is big or it is small. It has no effect on it. Now, we have described what we call orbits. There's something they call parking orbits. We have what we call parking orbits. So when you say parking orbit, you are talking about the curved part of an object in the plane of the equator. the curved part of an object in the plane of the equator. That's what we refer to as the parking orbit. Now, why can we have parking orbits? I want you to note this, please. It's very important. I think I've encountered a question on it before, and that's why I think I'm referring to it now. That can ask you that, when can we have a parking orbit? Parking orbits usually happen to what we call satellites. Are you getting it now? When satellite is at a certain position, and when will it be at that particular position? That's what they are telling you. That they may ask that, when is parking orbit said to what? Occur? Now note, a parking orbit holds or occur when the period of the satellite in its orbit, is exactly equal to the period of the Earth about its axis. Are we together now? You have parking orbit when the period of the satellite is what? Is equal to that of the Earth. So that's what we refer to as what? Parking orbit. All right? So, what are the examples of parking orbits? Let me give you like 2 examples of parking orbits. We have relay satellites. Relay satellites is an example of a parking orbit. Are we together now? And we have relay satellites. We have relay satellites for TV transmission. So for somebody that is asking for the benefits for TV transmission. So do you get that now? So we also have what? Surveillance satellites. That's another advantage of it. Surveillance satellites. So it helps you to give accurate value of weather condition. So for you to be able to get accurate value of weather condition, you must have what? A parking orbit. So for the person asking for the benefits, those are the benefits now. It helps you in TV what? Transmission. It helps you for surveillance. Are you getting it now? When you are trying to get right prediction for your weather. I believe we understand that. So let's wrap this up with the concept of weightlessness. Weightlessness. This is very important. It's another way why JAMB or WAHEC would like to ask you question under this particular topic. Weightlessness. Weightlessness. Now, when you say weightlessness, what do we mean by weightlessness? Literally, it is a psychological feeling. Are you getting this now? It's what? A psychological feeling. When a body is like empty, when you no longer feel the weight of your body, you are experiencing weightlessness. Are you getting this now? The psychological feeling that your body is empty is what we refer to as weightlessness. Now, this occurs when a body experiences the following things. I want you to pay attention to it, and I would like to break it down, because if JAMB wants to ask you a question under this, they can ask you that, they can give you an example like a man go into the space and then the man experience what? Weightlessness. What is responsible for that? Why do man experience that? Or a man in a lift, are you getting this now? Experience weightlessness. What might happen? Or a plane that is descending, people inside it experience weightlessness. What can result to that? Take note. Number 1, it occurs when the acceleration of a body is equal to gravitational acceleration. When the acceleration of a body equal to gravitational acceleration. The body will experience weightlessness. This is why when somebody is inside a lift that is falling freely, the person experiences weightlessness. Why? Because its acceleration will equal to acceleration due to gravity. Number 2, for you to experience weightlessness, when the resultant force acting on your body is 0. When the resultant force acting on a body is 0, then you said the body will experience weightlessness. Resultant force is given as mass times acceleration. Mass times acceleration. Sorry. Mass times acceleration plus mass times gravity. So if you have this, that will give you resultant force of the body. So anything that makes this one to become 0, then your resultant, you are going to experience weightlessness. And it will happen if A is equal to G. That means that MA is equal to what? Mg. So if you take this one in, you have MA minus what? Mg to equal to 0. You understand that now? So resultant force of the body must not be 0. If the resultant force acting on the body becomes 0, then the body is experiencing weightlessness. Are you getting it now? All right. So the third one is when the reaction on a body is 0. When the reaction on a body is 0. When the reaction on a body is what? 0. The body will experience weightlessness. And the last one is when the body escapes the gravitational influence. When the body escapes the gravitational influence. You understand that now? So when the body experiences gravitational influence, the body is said to be weightlessness. And that's why you see that people that are going into space, they always go with oxygen. Anything that makes your oxygen bags go away from you, that's bye-bye to that kind of relative. You can't see them again till the kingdom come. Because there's no gravitational force that will pull them back to the earth in space. So the higher you go, the smaller the gravitational force becomes. Okay. Now, okay, is there another name for weightlessness? No, I've not seen any other name for weightlessness. Weightlessness is weightlessness. Is that taken out? Now, example of where you can experience weightlessness, I've mentioned it earlier. When a body is inside a lift. When a body is inside what? An aeroplane that is descending. When a flight wants to land, you experience weightlessness. Are you getting this now? Object that is moving in orbit with the same acceleration and speed, you experience what? Weightlessness. Now, what I think jamb might want to bring that might be new to you is that what are the difficulties experienced when weightlessness is taking place? What are the difficulties experienced by that? It will be impossible for you to pour water into a cup. Are you getting this now? When there is water inside a cup, maybe you have a regular water and you want to pour it inside cup, it will be difficult. It will be impossible, not even difficult. It will be what? Impossible. And at the same time, it will also be impossible for you to drink from a cup when a body is experiencing weightlessness. All right? So to wrap everything up, let's compare mass and weight. Mass and weight. That's what we want to use to wrap the class up. So when you say mass and weight, what is mass? Mass is defined as the quantity of matter present in a body. Mass is defined as the quantity of matter present in a body. That's to tell you that mass is constant. It doesn't change. examiner can play with you a lot here. They can say a man is measured on the earth and it weighs 80 Newton. When the man is taken to the moon, what will be the weight of the, what will be the mass of the, oh, sorry, I said 20 Newton. Sorry, I want to say kilogram. 80 kilogram. So when the mass is taken to the moon, what would be the measure of the mass? Don't second guess yourself. It will remain what? The same.
80
Why?
kilogram.
Why? Because mass is constant anywhere. It doesn't change. Is that taken now? Now, what about weight? Weight vary. Why vary? Because weight is defined as the gravitational earth pull on a body. Weight is defined as the gravitational earth pull on a body. So it varies because it's depending on gravity. Remember, mass is constant, but gravity varies. So examiner can want to ask you, instead of them asking you directly that why mass, why weight vary, they can ask you that why is gravity not constant? Why gravity vary? So number one is because the earth is not perfectly spherical. Number one, because what? The earth is not perfectly spherical. This is what we call Budge effect. The Budge effect. So when I say Budge effect, what it means is that when you have this, and when you have this, and you have an object here, and you have an object here, the distance between this object and the distance between these two objects is not what? It's not the same. Are you getting this now? So that's what we refer to as Budge effect. It's one of the reasons why the acceleration due to gravity vary from place to place. Out there. The second reason is because of the rotation of the earth. So the rotation of the earth brings about the change in latitude. The rotation of the earth. The rotation of the earth. It brings about the change in latitude. And lastly is the change in altitude. Change in altitude. Let's take for instance that you measure the mass of somebody here. And you get to this point. And you measure the mass, the weight of the body rather. The weight here. The weight here. The weight you are going to have here will be greater than the weight you are going to have here. Why? The higher you go, the smaller it becomes. That is, when you are going higher and higher, acceleration due to gravity will be what? Reducing and reducing. So that's that about gravitational field. And that is how examiner would like to test you under this topic. Are we there now? So let's take some questions to wrap it up. Sorry, we always use more than the stipulated time. I think today will be the last time that we are going to do that. Sorry, permit us. We always want to explain everything. That's the problem we are having. All right, so question number one. So mind you, this question, all questions we want to treat, they are purely jamb questions. I decided to pick only jamb questions. There are other questions that I can use that are very tough, that make sense, but I strictly want you to get familiar with jamb questions only. All right? So the first question here, are you ready, guys? Please, if you are ready, let me know you are ready. But I know some people are tired already.
Yes, sir.
All right, thank you.
Yes, sir.
So the first question states that, which of the following statements is true of the universal gravitation? Which of the following statements is true of the universal gravitation? A, any two bodies attract each other with a force which is proportional to the difference in their masses. Is that true?
No, sir.
Okay. B, any two bodies attract each other with a force which is inversely proportional to the square of the distance between them. Is that true?
Yes, sir. Yes, sir.
Okay, so that should be our right answer. But let's check other options. Maybe there is one that is more perfect than this. Any two bodies attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of their distance, of the distance between them. Which one is more perfect?
Yes, sir. This one. Yes, sir.
More
E.
perfect.
So
C.
it means we can't go with this option. So
B is the answer, sir. I go with B.
listen to B
So I
very
go
well.
with C.
Listen to B. Any
I
two
go with
bodies attract each other with a force which is inversely proportional to the square of the distance between them. And C
Yeah, that's
say
the
any two bodies attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. So if you look at
So I go with C.
this, the first one, it only stated the first part of the law. Are you getting this now? Sorry, it only stated the second part of the law. It doesn't state the first part of the law. But if you look at this second one, it stated complete law. And that's why C will be the right one. So what JAMB wants to do here is that they want people that know it, but they are too in haste to pick answer. They want them to get it wrong. That's why you need to check all your options before you settle down for one. Even when you see the one that is certain, check others. They might be most perfect one. Do we understand that now, guys?
yes, sir.
Yes, sir.
All right. So we'll move to the next question. And that's question number 2. Now, pick your pen because this might have to do with calculation. So pick your pen.
Sir, please can you zoom the question?
Okay. Okay. Can you see it clearly now?
Yes, sir. Yes, sir.
Yeah.
Thank you, sir.
Okay. So the question states that a planet has mass m1 and is at a distance r1 from the sun. A second planet has mass m2, which is equal to 10 of m1, and is at a distance of r2, which is equal to 2 of r1 from the sun.
No.
Determine the
No, I'm not
ratio.
seeing it.
Is that what? Determine the ratio of the gravitational force experienced by the planets. So can we solve now, please?
Sir, 1:5.
1:5. Is that what everybody gets? Who is solving? Any other person? Do we all settle for that answer? 1:5?
Sir, yes. Yes, sir.
That 1:5 is the right answer. Okay. Do we have any other answer different from that? Okay, let's solve it together. I'm questioning that 1:5. Doubting it because I know that if I square 2, I will have 4. But let's go on. Let's see. Are we together?
Yes, sir.
Okay. A planet has mass m1. Let's say planet A. Let's say planet A has mass m1. And it is at a distance r1 from the sun. So the mass of the sun, let's say it is capital M. And the distance between the sun and the planet A is given as what? R1. Are we together? So before we continue the question, let's first of all find this. So the force of attraction between the sun and this planet is going to be what? GM1 all over R1 squared. So let's call this star. I'll call this F1. Now, a second planet has mass M2, which is equals to what? 10 of M1. So the second planet, let's call it planet B. Let's call this one planet B. The mass of planet B is 10 of M1. And is at a distance of R2, which is equals to 2R1. So the distance of this planet away from the sun is given as 2 of R1. So let's find the force of attraction of this also. So FB is going to be G of what? Capital M. So its own mass is going to be 10 M1 all over. Its distance is going to be 2R1 all square. You guys agree with what I'm doing?
Yes, sir.
Yes, sir.
So the question now states that determine the ratio of the gravitational forces experienced by the planets. So let's look at the ratio of FA to FB or FB to FA. So we are going to have that FA divided by FB is equal to GM and small letter m, that is M1 over R1 squared divided by FB is that's what? Let me just put the 10 outside. So that will be 10G M and M1 divided by 4R1 squared. So the ratio of FA to FB is going to become GM1 all over R1 square multiplied by 4R1 square divided by 10 GM1. Are you seeing it now? So GM will cancel GM. R1 square will cancel R1 square. So we are left with F1 ratio FA ratio FB is now equal to, remember this, okay, M1 would also cancel M1. So you are left with just what? 4 over 10. 2 here is 2 and 2 here is what? 5. And that will be 2 ratio 5. So you must have made a mistake of probably not squaring the other value. That should be the reason why you are arriving at 1 ratio 5. I believe you have taken the correction. So the correct answer is what? B. You guys understand that so that we can move to the next question?
No.
Yes.
Okay, what is it that you don't understand?
Okay, sir, please can you take it back up a little?
You find here?
Yes, sir.
Okay.
Okay, I understand.
You get it right now?
Yes, sir.
All right. So we'll move to the next question now. And that'll be question 3. So what does this question state? Sorry. So the question states that an astronaut, are you listening? An astronaut experiences weightlessness in space when he A, does not hold anything while in space, is midway between the sun and the earth, is free from the earth's gravitational field, D is walking on the moon.
C.
C
C.
is
C.
free from the Earth's gravitational field. And that's correct. So we'll move to the next question. Question 4. Okay. Kind of similar to the first one we have. So the question says that two bodies have masses in the ratio 3:1. They experience forces which impacts to them accelerations in the ratio 2:9 respectively. Find the ratio of the forces the masses experiences. So we're solving. I hope we'll start solving it of time. Let's do fast. We have just 10 minutes. I'll get an answer from anyone.
Sir, I'm getting 2:3.
2:3. Is it part of the option?
Yes.
Okay, so let's wait to hear from others. Cross check your work. If you are sure of it, then we can stick to it first and wait for others to respond also.
So I go with her 2:3.
Okay, you go with our 2:3.
Ratio 3, yes.
All right. I think that answer is correct. So do we need to solve it, or we all understand how they arrive at that answer?
Please solve it, sir.
All right. So let's see. We are told that two bodies have masses in the ratio 3:1. So let's say m1 divided by m2. They have 3/1. Are you following? They experience forces which impacts to them accelerations in the ratio 2:9. So because we are dealing with what's it called? Gravitational field, I'll let that their acceleration be what? Acceleration due to gravity. So that will be g1 over what? g2 is equal to 2/9. Find the ratio of the force. So for us to get the force, we recall that force is mass times acceleration. Am I right?
Yes, sir.
Okay. So that means that the force experienced by F1 and the force experienced by F2 is going to be the product of their masses. M1 over M2 multiplied by G1 over G2. And this will give us 3/1 multiplied by 2/9. So 3 here 1, 3 here is going to be what? 3. So you have that F1 over F2 is equal to 2/3, which is the same thing as saying 2:3. You understand that now?
Yes, sir.
All right, so let's take just one more question and you take the rest as assignments. So question 5, Abby. Yeah, question 5. All right, so the question states that the gravitational force of the moon is 1/6 that of the earth. If a body weight is 6.0 Newton on the moon, calculate its weight on the earth. What will be the right answer to that?
Sir, please can you zoom the question a little bit?
Okay. Listen it clearly.
Yes, sir.
Sir, 36.
36. Okay. That's option A. Any other person?
36.
Another person got 36 also.
36.
Okay. So that's absolutely correct. So 36 is the right answer to the question. So thank you guys for making it to this class. By His grace, the replay will be available first thing tomorrow morning. If not this night, you get it tomorrow. You should be able to get it this night so that you can watch. Like I told you, this week class is going to be free, general for people to watch on our YouTube page. Starting from next week, they won't be able to watch again, but you will still be having access to replay for those who missed the class. Thank you so much for letting this program be a dream come true. And I pray that God will use it as a means of success for every individual. I so much appreciate our presence. So I'm going to drop the assignment. That is, they'll practice questions about maybe 15 or 18. I can't really recall. I'll drop it on the group. So give it a try, submit so that I can mark and you know where you need to work on. Is that taken now? So see you guys on Saturday. And remember, Saturday is going to be a lengthy class. We are starting by 10 o'clock in the morning. And we just continue like that till probably 4 o'clock in the evening. And that should enable us to cover enough topics. Are you getting it now? And that's how we are going to move. So before you get to know, we are done with this part and we must have covered virtually all the topics in jamb. And that's how we are going to do for chemistry, mathematics, and then biology also. So I wish you guys
So, sir,
success.
please, when will the chemistry class and biology class start?
Our biology class is going to start by chemistry class is going to start next week Thursday. And biology class is going to be next week Saturday. So biology stroke
No
mathematics.
matter.
I getting this now. Biology stroke
The physics
mathematics. So when biology is going on, mathematics will also go on simultaneously with it.
Sir, how will it be done? Will it be the same? Sir, how? How? Be biology student now. Where are we going to have our class?
If you are a biology student, there's a link for biology students and there's a link for math students. So
Okay,
so
sir.
after Saturday class, I will.
So once you are it's going to be Saturday class, but not this Saturday, upper one. So when you are if you're a biology student, the link for biology will be dropped, so you join biology class, and the link for mathematics class will be dropped, so you join math class.
But it will
After
still be the
Saturday,
same Google Meet we use.
Yeah, it's still going to be Google Meet, and it can be a biology class might be on Telegram, depending on the instructor.
Okay, sir. Thank you, sir.
Welcome. Any other
after
question?
physics on Saturday, we haven't finished.
Now, after physics on Saturday, you are still going to be having physics every Tuesday. You understand that one?
Yes, sir.
All right. Thank you, guys. Do well to practice well. Jam will be easy for you when you are familiar with a lot of questions. All right, guys. So see you in the next class on Saturday. And please invite your friends, let them join this program. It's going to be a good help for them also. We need more population so that it can keep the spirit alive. Thank you, guys.